Thanks so much for joining me on this beautiful afternoon. I hear we're getting some not so great weather tomorrow, so I'm happy you're here to take advantage of the day. My name is Kim Arcand. I work for NASA's Chandra Observatory. I've worked there for almost 21 years. I was part of the mission before it launched, but before that, my husband is on technical duty forwarding the slides, so you're going to see me pointing to him like Vanna White. Thank you, hon. I actually did my undergraduate work at the University of Rhode Island in molecular biology. I was very interested in this idea of parasites and what they could essentially give to humans. I was studying things like this. Does anyone know what this is? Yes. Does anyone know what kind of tick? Deer tick, exactly. Well, it was an excellent guess. Ixodes scapularis. This is the deer tick that can give us Lyme disease if it's connected to human tissue for 24 to 48 hours. Those bacteria from its stomach can get into our bloodstream and then turn into a very difficult illness. So, though I was really fascinated and I was looking at things like this under the microscope to study its stomach contents, I started realizing that that's not what I wanted to do with my whole life. So from there, I went into computer science. For me, the transition was actually very natural. There's a really big need to be able to take the data that we have in science and do something with it using computer science. So that brought me here working for the Chandra Observatory. Click. NASA. So the Chandra Observatory is one of NASA's great observatories. It was launched back in 1999. It's about the size of a school bus. It was actually the largest payload bay ever launched. Chandra studies things, oops, nope, go ahead, hon. That's fine. You could have just, I'm going to flow with you. How about that? Go back up one. Wait. Yeah. All right. So Chandra is the size of a school bus. It's an amazing piece of technological equipment. Even to this day, it is really cutting-edge technology. In order to understand and being able to capture X-ray photons, we have to have very special technology in order to do that. The way an X-ray telescope actually gathers images, or gathers data of our universe, is instead of a flat mirror like you have for an optical telescope, it actually needs what are barrel-shaped or nested mirrors that the X-rays just kind of skim along. Like if you take a stone and skip it across a pond, that's kind of what you think of when you have X-rays that you're trying to get down to the detector on the spacecraft. The technology that went into making Chandra was absolutely ahead of its time, and today we actually are the benefactors of many technological spin-offs from this one observatory. Just so much achievement had to happen in order to launch this one spacecraft that today we have better MRIs, we have better mammogram machines, we have better food quality control systems, we have better airport security, tons of actual human technological advantages due to one single spacecraft. On our next slide, these are actually the astronauts that launched Chandra. We owe them quite a debt of gratitude because Chandra being so heavy at 4,800 kilogram mass, it was the largest payload that the Space Shuttle Columbia or any space shuttle had ever taken up into orbit. Now what that meant was because it was so heavy, the abort scenarios for the astronauts in case they had to come back to Earth with Chandra still in its payload bay were actually much more dangerous. Eileen Collins, the woman on the lower left, she was actually the first woman to command a NASA space mission, and when I asked her how she kind of treated that idea of having a very dangerous mission, she was so calm, cool, and collected about it, and she just said, we trained really hard. We knew that system in and out. We knew all the things that would have to happen, and we had complete trust in the control operators that were going to be down in Houston at the time. Fortunately, there were no true issues with the launch, and Chandra was put into space and now gets to study the high energy universe. So things like exploding stars, which are my personal favorite, and that's what I'm going to talk about today. Things like the areas around black holes, and things like colliding galaxies. Now, on our next slide, we're going to just go back really quick to the molecular and microscopy type of world. So this was what I was studying before Chandra. These are the actual spiral-shaped bacteria that are in the stomachs of ticks that can give us Lyme disease. So here we're working at around 10 to 25 micrometers long, each little piece. If we go to the next slide, now this is what I get to work on today. This is a pair of galaxies that are interacting called the antennae galaxies. And here it's about 400,000 light years across from corner to corner, where a light year is the distance that light travels in a year, which is about 10 trillion kilometers, give or take. I'm definitely having a lot of averages here. So the difference in size between what I used to look at and what I look at now probably seems pretty extreme. However, when we look at the similarities between what we see under a microscope and what we see in space, there are more similarities than you might think. Now, all of these things that we're looking at here, we cannot see with the human eye. The human eye, as amazing and magnificent as it is in general for our existences here on Earth, is really kind of puny and inadequate when it comes to the greater world, both the universe at large and the universe under a microscope. We can't see any of these things directly as we would with human eyes, so we have to use scientific instruments in order to help create these images. So we're going to have a little game. If we look at this pair of images on the left and the right here, which of those images is the big one and which one would be the small one? Anyone want to take a guess? The one on the left is the big one, and do you know what it is? Exactly. And guess is what the one on the right is? They're Raji cells, which can actually lead to Epstein-Barr syndrome. But you can see there's a beautiful sort of symmetry just between those two images, right? Not just the color, but also just kind of the general shape and makeup. Let's look at one more. How about this pair here on the lower left? This one and this one. Does anyone want to guess which one's the bigger one?
I say the one on the right.
The one on the right? You win 500 points. Yes. So the one on the right is an example of a star that's exploded. The one on the left is actually onion skin cells. Yep, onion skin cells. Yep, literally from an onion. Super tiny, but onion skin cells. Yep. So my point in showing this is not, to kind of feel like you're tricked or something, not knowing which is which, but just to show the beautiful similarities between something that's really, really small and something that's really, really big. Next slide. That brings me back to the really, really big. We're going to take a little quick journey through a number of different stars. I like to concentrate on stars that are dead. They're really fun. And stars that are dead sound very depressing, but they actually lead to future generations of life. So we're going to see a few more examples of that. But first, before we do that, I just want to essentially give a primer on the different kinds of light that we use in astronomy. This is an image of our sun, exactly. And it looks weird because, any thoughts? Yep, exactly. You're seeing one mission from NASA, NASA's Solar Dynamic Observatory, and all of the different lights that it can image our sun in. So one spacecraft looking at one object, right? And these are all the different kinds of light that our sun emits, from infrared and X-ray to ultraviolet and everything in between. So the point is that in astronomy, using all of these different kinds of light, it's really important. Each kind of light is like a different tool in the astronomer's toolkit. I really do feel like Vanna White pointing at my husband. It's just, thank you. So we have the electromagnetic spectrum. And as you can see, we have different spacecraft that look at different kinds of objects in the universe and different kinds of light. And studying all of these different kinds of light is really important. You're also probably familiar with many of these kinds of light as well. If you use a microwave to heat up dinner sometimes, anyone? Anyone? Yes. So you're using microwave light to essentially disturb the water molecules in your food to make them heat up really fast. If you've ever had an X-ray at the dentist or the doctor, if you've ever broken a bone or have a cavity, anyone? Anyone? A few? I feel like more people should be going to the dentist. If that's, yeah, okay. I'm a little worried about your teeth right now. So you are using, essentially your doctor is using X-ray light to be able to look through tissue and bone and down into the center of the bone and see what's going on. Also remote controls, if you ever use a remote control to like turn on a TV. So you're using infrared light to talk to your devices. The point is there's all of these different types of light in the universe and they're all really important for doing specific things. So can anyone tell me what this is? I think I heard it. Yeah, what is it?
Baseball field?
Yes, but what part? Can you tell me?
Third base.
Yes, exactly. So it's just a tiny sliver down the third base line, right? Now, this is the equivalent that if we could only see the universe with our sad, puny human eyes. This would be the amount of the universe that we're catching a glimpse of. Now, if you don't know how to play baseball, how hard is it going to be to understand the game, right? If you can't see the field, how are you going to know who's winning? I mean, I guess you'd see someone running down to the home plate at some point, but it's going to be really hard to keep track of what's what, right? You can't see the pitcher, you can't see who's on first, who's on second, whatever. You can't see anything, right? Next slide. Go ahead. One more. Thank you. So now that you see the entire baseball field, you have a much better chance of understanding the game, right? Now, I'm not a sports person at all, so sometimes when I use this analogy, I feel a little ridiculous because I probably don't know half of the rules in baseball, but I kind of feel that's actually a good example because just like in the universe, you can watch something and get a sense of things, but you'll never know everything. So another analogy that we can do, anyone here who plays a piano? No one plays a piano, really? Oh, wait, there we go. Cool. All right, so what key do I have highlighted here? Yes, all right, middle C. They answered for you. So if we could only see the universe with our human eyes, it'd be like only being able to play middle C and maybe one or two keys on either side, right? So what's your favorite piece to play on the piano? Something grand, perhaps, or something small? Just anything. Anything? All right, so think of a piece by Beethoven. How would that piece sound if you could only play 3 keys in order to hear that music? You'd be missing that symphony, you'd be missing that full, beautiful sound, right? The analogy here is that we'd be missing all of the music of the universe if we couldn't see it in all the different kinds of light that exist. All right, so we're going to start talking about dead stars. My absolute favorite thing, as I mentioned before, in stellar evolution, stars are all different sizes and different kinds. And a lot of stars that are really massive, like 10 or so times larger than our sun, or at least perhaps even bigger than that, when they die, they go out with a bang. And essentially, as a star ages, it starts to run out of its nuclear fuel, and when it's really massive, all of that kind of material is changing and it's coming down into iron, and then essentially the core is so heavy it just collapses. And when it collapses, then the star explodes. So this is the aftermath of a star that's exploded and sort of vomited its guts out into the universe, right? We're looking at this object. It's called Cassiopeia A. It's about 10,000 light years away from us, so 10,000 times 10 trillion kilometers. That tells you how far away it is. We're looking at, with optical light from the Hubble Space Telescope, we're seeing beautiful, delicate filamentary structure. This is showing material around the 10,000 degree mark. We can look at the same field of view with the Chandra Observatory, same exact patch of sky that we just saw in the previous slide, and now we're seeing death come alive. This is the star that's exploded, that now you're seeing the high energy material from that star. You're seeing material that's in the million degree range. And you can see in this image, we've actually color-coded it by the type of chemical element that's inside it. So the iron, the silicon, the argon, the sulfur, all of those kind of create this beautiful color map. But you can combine the two images together, and you can see where the optical and the X-ray data overlap, and then you have a better picture of what it is this object is doing and what it is you can learn from it. But images of the universe don't start out looking like the perfect one that we just saw before. They start out looking a little bit more like this, or a little bit more like this, but really they look more like this. So what is this? Binary code, exactly. So we use binary code, which is a system of ones and zeros, to talk to all of our spacecraft. We also use it to talk to our phones, to talk to our laptops, but usually that type of information is invisible to us because we're seeing and utilizing software that runs over top of it, right? So this is a tiny snippet of the ones and zeros that actually were created into that image that you saw previously. This is actual data from Cassiopeia A. So When we are observing an image, we have our image in outer space. That light has been traveling for some time. We have our trusty spacecraft, which in Chandra's case goes about a third of the way to the moon. Chandra observes that information and collects it in its scientific instruments and then transmits it down through NASA's Deep Space Network. There are a few dishes across the world. That information is then brought to the JPL, the Jet Propulsion Laboratory, before eventually it ends up at the Chandra Operations Control Center, where I work in Cambridge, Massachusetts, or sometimes if I'm in Rhode Island, or sometimes if I'm traveling. The good thing is when you have a spacecraft that goes a third of the way to the moon, you can kind of work anywhere because it doesn't really matter. But this is essentially the data path, right? So next. When we first get those ones and zeros, the step that we do immediately is to translate them back into a table of information that gives us a little bit more of an idea of what's going on with this object. So you can see for each of the observations, we have the time, we have the location in X and Y coordinates, and then we have the energy. Then we take more scientific software and we translate that into a visual representation of the object, right? These are truly not space selfies. We're not just taking a CCD, pointing it up at the sky, click done. You have to have a person in there in order to do the visual representation creation. I'm going to talk a little bit about the details of that more. So we have an image that looks like this. This image has been smoothed a little bit. If there's bad data, the data has to get tossed. We have to understand the field of view that we're looking at, so we'll have to crop in sometimes. And then one of the last few steps we do after we smooth it out and bin it out is to add color. So you can see, click, 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 there. So you can see what we've done in this case is to actually cut the image into thirds by assigning the lowest bank of X-rays, the lowest energy X-rays to red, the medium energy groups to green, and then the highest energy group to blue. And when we combine those three colors, we get a red, green, blue image that looks something like this. So it's a little bit like on the nightly news when you're looking at a weather map and you see a temperature map for the next day's temperature, right? And you're going to see some areas are maybe blue and maybe some are purple. I don't know, depending on what the meteorologist is using for colors, you'll see a color map of some sort, right? It's the same idea. We are color coding this object loosely by energy, by temperature, if you will, in order to understand what's happening where. So you can see where is a lot of the high energy X-ray appearing. Around the edges, exactly. So what that means is this outer edge is essentially the expanding shock wave of that supernova as it's traveling out in space and then hitting that interstellar stuff, the interstellar medium. And that lights up into this high energy shock. Then you're seeing the lower material, the lower energy in reds and greens, and you see pockets of them here and pockets of them there. And it gives you like a really useful map to understand what's going on. Next slide. Instead of color coding just by temperature, you can, as I mentioned earlier, also color code by chemical element. So you can assign colors to your iron, to your calcium, to your sulfur, to your silicon, and then get an image that looks like, click, that, which I showed earlier. This just gives you a different kind of image map to look at. Now you're seeing that over here, there's a lot of this purple color. That's a lot of the iron. And what that means is when you look at a star that's exploded, this, by the way, is the leftover core of that star. It's a neutron star. And like just a teaspoon of that material probably weighs as much as like 1 million elephants. That's how densely packed the leftover bits of that star happen to be. So when you see the iron, which used to be at the very, very core of the star right before the explosion, has made its way all the way out to the perimeter. What that tells you is that stars like this one, Cassiopeia A, when they explode and they vomit their guts out into the universe, they turn themselves inside out in that process. So the material that was innermost in the star's core are now all the way out at the edges and the perimeter. We have no idea why they do that. No idea. All right, our next slide. So now I just want to take us a step past 2D data and show what happens when you have a telescope that's been up for a long time. In this case, Chandra has been up for 20 years. We have a fantastic archive. It's like a treasure chest in there. And if there's one thing that NASA archives are really good at, it's like incredible data organization and control. So we have this fantastic data archive for Chandra. And when you take different observations of an object like Cassiopeia A, our supernova remnant friend that's 10,000 light years away, 10,000 times 10 trillion kilometers, you can see it changing over time. So I think when people see images of the universe, you see this one static image, and it's very easy to think that these objects are so massive and they just kind of stay the same and they're just static, and that's how the universe is. But the universe is moving and evolving and changing all the time. And when you can help communicate that through a time-lapse movie using actual data, you're just helping to show what happens when the universe is evolving. But there's scientific merit to something like this as well. It's not just about the visual, but it's also about understanding what's happening in this system. And what we learn here is that outer shock wave that I mentioned, this blue part that we're looking at here, that's traveling outward at around 11 million miles per hour. That's pretty fast, right? And you can help see that just by looking at this one time-lapse movie. But we weren't quite happy enough having just 2D plus time. In our next slide, we took the same data and we were able to map it into a three-dimensional model. So this is using the real NASA data of Chandra X-ray Observatory data, but also from the Spitzer Space Telescope and some ground-based optical telescopes. When you take all of those different kinds of light together, you can understand what of the remnant is moving away from you and what of that supernova remnant is moving towards you. And that's essentially using some math. If anyone likes geometry here, we use a little geometry. We understand that this star is, expanding from a single point in space, and then also the Doppler effect. Is anyone familiar with the Doppler effect? Right. So can anyone do the sound of Doppler effect change me? Because I'm really bad at it. Anyone? All right, good. Wow, very nice. Okay. So what the Doppler effect tells you, right, is think of an ambulance. If the ambulance is far away, you'll hear one version of the sound, and as the ambulance gets closer, yes, the volume changes, but also the pitch changes, right? So that change in sound, you can think of it the same way. We're just using it in a data form here. So what's red shifted and moving away versus what's blue shifted and coming towards this. So this was the first time, just think of this for a second, right? This object is 10,000 light years away, right? Unlike an object here on Earth that we want to do a 3D scan of. For example, President Obama. When we had some Smithsonian folks sit him down in a room, they had a ring of cameras that zipped around him, and within maybe about an hour, they had a perfect 3D model of President Obama's head that they could then 3D print out. You can't do that in space because these objects are so far away from us, right? So we have to use very interesting techniques and a lot of math in order to figure out how to represent this in three-dimensional space. So this is taking that same version of the data and then just applying some textures that look a little bit more spacey. The previous version of the 3D model, we actually had to use brain imaging software because at the time we didn't have any of our own astronomical software to make it. So we took it into a professional platform here and applied some textures. So this is the same star, Cassiopeia A, 10,000 light years away, and you are seeing above, below, behind, and through that exploded star that threw its guts out into the universe. The calcium, the silicon, the iron, all of that amazing stuff. And you get to see where it is in a 3D space. The next slide. We weren't quite happy with just having it on a screen, however, so we figured out how to 3D print from our trusty Smithsonian friends that had 3D printed President Obama's head, and figured out how we could hold a dead star in our hand. Now, here's a 3D print. I'm going to pass it around. Now, this is about 4 inches across, right, including its jets. In reality, Cassiopeia A is about 40 million billion times the surface area of our sun and planets, and you can toss in Pluto and a few asteroids if you like. At that scale, it doesn't really matter. But 40 million billion times the surface area of our sun and planets. And that's how big this object is in reality, right? So this is a very, very, very tiny version of it. I'm going to pass it around so you can all hold a dead star in your hand. Just try not to drop it. It takes me like 2 days to 3D print it. But don't worry, if you do, it's okay. I won't cry, I promise. All right, on the next screen. So this is a version that we 3D printed, and I was very excited to have this. For once, To be honest, when I first 3D printed it, I just thought it would be cool. I wanted to see what would happen if we 3D printed this dead star, and I loved it. But then I realized that people who do not have sight, now it meant that they could actually touch a part of the universe and touch an actual mathematical map of information in the universe. They could feel what I get to see every day. So something that started out just for fun has actually become an incredibly useful tool to be able to communicate with different people. On the next slide, you'll see the previous version, and what I'm passing around is just a single color. But what we eventually figured out to do is how to take the multicolor and do a 3D print of that as well. I didn't bring that one with me because it's a little expensive, and I only have a few. But it's a really useful tool to be able to see all of the different colors and understand more about this exploded star, right? So by creating these 3D models, we have versions that we can use when we're communicating science and use with different audiences, sighted and non-sighted audiences, but also scientifically it gives us more information on stars like this. So we know when a star like Cassiopeia explodes, it comes off in these two pieces. It comes off first in this spherical sort of shell-like component, and then second, these really strong fiducial jets that kind of jut out at opposing angles. And you'll see the jets as it's passing around to you, hopefully if they don't fall off. They're a little fragile sometimes. But on the next slide, you'll see we decided to take it one step further, and one day I just happened to randomly come across this fantastic 3D VR laboratory at Brown University. And this guy that was giving me a tour of the lab had a little piece of Mars up, so I got to walk on Mount Sharp on Mars, and I thought, well, I have 3D data. Couldn't I just bring my 3D data to your lab? And he was like, yeah, and we did. And this is what happened. This is one of my students experimenting with the model, but you can see the camera person is actually outside of the remnant, but she is inside it. So she is walking inside a star that exploded, our good friend Cassiopeia A, 10,000 light years away, 10,000 times 10 trillion kilometers, she's walking inside it, right? That gives you such a different understanding of your information than when you're just looking at a flat image on a screen, right? It really does help you learn different things. The first time I ever walked inside this model, I saw this clumpy area kind of underneath this iron. I had never noticed it before. I have looked at this image. Cassiopeia A was one of the first images that the Chandra X-ray Observatory ever looked at. So I have literally been looking at Cass A data for 20 years. And the first time I walked inside this virtual reality model, I noticed something completely different. So I think it's a really interesting way for us to understand the universe. Where this will go, I don't know. One of the things that I'm working on now is to take this and add a layer of data sonification so that you can hear the bits of information as you're walking through it, particularly useful for people who are visually impaired that cannot see the virtual reality version, and also adding a layer of haptic technology. If anyone have like a phone, and when you get a message and you have your volume shut off, it vibrates. So you can actually use that same vibration technology on your phone and attach the spatial information in that 3D model so that as you're walking through it, you'll feel the vibrations change. So it's just another way to understand all of this amazing data. If you click to the next slide. Oh, that's just one of my other students inside. Click again. This is a version of the 3D model so that if you don't have access to virtual reality, you can actually use the controls, which you can't really see the picture for some reason. It's a little dark, but you can actually work on the controls and change this remnant in 3D space. This is a free URL. I'm going to give you the URL at the end if you want to play with the data yourself. On the next slide, you'll see I've talked about this one object, just one so far, really. Cassiopeia A, our good friend, 10,000 light years away, 10,000 times 10 trillion. And we're looking at all of these versions of it, but they all came from the same bits of data, right? This great data set that we've been collecting over 20 years of one mission. All right, in my next few slides, I'm going to talk about another supernova remnant really quickly. I don't want to take up too much time on this object, but I did want to talk about others so you can see this was not a one-trick pony. Getting three-dimensional information of our universe is hard. but we're starting to understand how to do it better. Supernova 1987A is another star that's exploded. This one is much farther away than Cassiopeia A. This is about 160,000 light years away. So you can see the resolution is not quite fantastic on it, but it's still, we're learning a lot of information. So 160,000 times 10 trillion kilometers, it's pretty far out there. To be able to even see this well of this object is exciting. We can look at this object with all of our different kinds of light, as we were showing before. This is optical data, X-ray data, some infrared data, and a little radio data. And we can see this object changing over time. This is a time lapse of the X-ray information. What's happening is, when the star was getting ready to explode, it had a little temper tantrum and kind of sent out this big burp. And that burp just kind of stuck in space in a ring around the object, so that when the star finally did go supernova and explode completely, all the material kind of rushed out and then hit that existing ring and lit it up. Now you can look at this object. It probably doesn't look super exciting to you. It was very exciting to us, but I know it doesn't look it, but hold on. If we go to the next slide, this is that same data that we're now going to look at in a 3D space. So there's our ring being lit up after the supernova went boom. And turn that ring on its side, and you now see there are all these fingers of gas and dust. So if we go to the next slide, that's a cut of it. So what we're seeing as a plain donut from the front, this is what it looks like from the side. It's a completely different view. And we skip to the next one. This is what a 3D print of it looks like. Now think of that plain donut I showed you just a few slides ago. But this is what this object actually looks like when we're able to model it in more dimensions, right? And from different angles. We've actually turned this into virtual reality as well. I don't think I have a clip of that here. Oh, yep, this was one of my students working on creating the virtual reality application in Unity. And that's him fiddling around with the dials. So this was the first time that we had a virtual, so the Cassiopeia A supernova remnant was the first time we ever 3D modeled anything like that, right? This was the first time we were able to take data in 3D over time. So adding time to that virtual reality model. Our next slide. I'm going to show you one that's in progress because, again, I mentioned this kind of work is hard, right? We cannot zoom out there in a little spacecraft and like get a nice 3D picture of these objects. We have to use a lot of really cool technology and good math. Tycho's supernova remnant is a famous supernova remnant. Tycho, actually, the scientist observed it back in like 1572, I think. A beautiful X-ray image that we're looking at here. You're seeing a similar accelerated shock all the way around in blue. And then this red and green kind of material, all superheated hot material throughout the remnant. We click next. What we're able to do is find about 50 to 60 points of that data set and understand which of those are moving away from us. So if we click to the next movie, and there we go. So by pulling each of those 50 points and understanding where they were in relationship to us, you can dive in to the supernova remnant. Now we only have about half of the data that we really need to make a true 3D model so far. So you'll see it stops like about 3/4 of the way through, and then you're going to back out. So a two-dimensional image that looks solid and flat is really not, right? It has information in a 3D space. You can see as you're going through it, some of those little clumps of material are much farther in, some are much farther away. So looks can be deceiving, essentially, right? What looks solid is not. The density of things like this, it's probably at a max about, I don't know, maybe 100 little electrons per cubic centimeter. It's a very nebulous, pun intended, porous type of object, right? And it looks solid just because of the way we have to image it from afar. But by being able to look at these in 3D spaces, we understand and can help show how these objects are not these solid, perfect things. Next one. So why do we care about things like exploded stars? Well, I just think they're gorgeous, but they're also really useful for understanding our sort of cosmic origins. Previous generations of stars that have exploded essentially are the reason that our bodies have iron in them and the reason that we have silicon and other materials at our disposal. So the calcium in our bones, the iron in our blood, that comes from previous generations of stars just like Cassiopeia A that exploded, and that material is then swept up into new generations of star stuff, new generations of planets, new generations of stuff that made people. The next slide. I'm just going to show two things that are not dead, because I feel like sometimes I look like I'm very goth when I'm giving a talk, because all I talk about is dead stars. But I do like to say, one, of course, these stars, though they are dead in and of themselves, they go on to create new generations of stuff, as I just mentioned, so it's a beautiful cycle. But also there are other types of objects that we can look at. This is an example of a star that has not yet exploded. It will someday, but don't worry. It probably won't explode until like 50 to maybe like 50,000 years from now. This is called Eta Carina. It's far enough away from us that we will not get bothered by any radiation from it. However, if it does explode in our lifetimes, we will see it during the day. It'll probably be bright enough to be visible, like you might be able to see like a planet even. And it's a beautiful star. There's actually two stars inside that little clump of material right here. When you're looking at it from just a simple 2D angle, you don't really get much of a sense. It kind of looks figure 8-ish. If you go to the next slide, you can see that we were able to model that nebula into 3D space, and so you can understand what's going on. There's the transition between the 3D and the 2D. On the next slide, this is a very famous image from the Hubble Space Telescope. Probably some of you are familiar with it. It's M16, or the Pillars of Creation, a beautiful structure where baby stars are being born. In each of these pillars of gas and dust, there's tens and 20s, if not hundreds, of stars being born. I would say maybe that tallest pillar is about 4 light years tall, perhaps, so 4 times 10 trillion kilometers. And this is beautiful, but again, you're seeing it from just one angle. So when we look at it in a 3D map, you can see that those pillars are actually separated from each other in space. And it's just the viewing angle that we have from our perspective here on Earth that makes some of them look larger versus brighter versus more pointed towards us. It's just kind of a trick of the light. So these are baby stars, so that's good. No death there. Next slide. You can see the comparison between the flat image and the 3D map. So if you're at all interested in 3D printing, by the way, and if you have a 3D printer at your school, your makerspace, or whatever, this URL at the bottom brings you to a really large library of 3D models. All of the models that we've worked on are all in this overarching NASA 3D database. So you can download them and you can 3D print them, or you can play around with them and make images out of them, whatever you're into. Virtual reality if you're into that, augmented reality, you name it. On the next slide, I'm going to talk just a little bit about color. So I think I talked about that human aspect of the image creation process, right? These images are not made by computers and software. We have to use software, we have to use technology in order to make them, but there's always a person sitting behind that computer making choices as to what to show and how best to show it. If we go to the next image, this is an example, NGC 4696. It's an elliptical galaxy, maybe, I don't know, 160 million light years away, something like that. So 160 million times 10 trillion kilometers. It's a beautiful object where there is this supermassive black hole right in here. It's sending out all this material that's calling, like it's resulting in some cooler radio lobes here, and then this hot plume of superheated gas, which is this massive amount of material that goes all the way out of the galaxy. Beautiful object. This is the version that we ended up going with, but we can see on the next page, this is the version that we originally had. When a scientist is making an image, typically they're going to assign the lowest energy to red and the highest energy to blue, because that's physics, right? But when we think of color and what kind of cultural value it has to us on a day-to-day basis, what means hot to us here on Earth? red, exactly. I don't often hear a parent say to their kids, don't touch that stove, it's blue hot, right? That doesn't happen. But if you look at a flame, what part of a flame is the hottest? The blue, right? You'll see the red at the bottom and you'll see the blue up top, and that blue top part is superheated. So if a physicist is making an image and this material right here is very hot, he or she may want to color it blue, but if we go up, wrong way, there we go. Thank you, honey. We ended up reversing the color scheme for this object because it was so important to talk about the heat that was coming out from that supermassive black hole. All of that amazing high energy material that when we showed it in blue, it kind of looked like an iceberg with a little lava flow on the top. And that was the exact opposite of what we wanted to show. This material is the coolest and this is the hottest. And we wanted to be able to show that using color that people are familiar with. Because if you're seeing this object out in the internet universe somewhere, right, and it's not attached to anything, any text perhaps, it could immediately say cold to you. So we wanted to make sure it had a little bit more cultural awareness. If we click down, yeah. All right, so why do I have this lady on my screen? I have to, on my laptop, bring up a little thing to say about her. So another thing that I like to talk about essentially is context. This is a painting. Does anyone recognize this painting? I don't think I've ever asked that before. No, I didn't know it either, so don't feel bad. This is Madame Henri Francois Raisonnet, and it was painted in 1835, oil on canvas. Now, if I love art, by the way, but I am not like an art expert by any stretch of the imagination. I like to go to a museum, look at some beautiful art, and then be like, cool, I got some culture in today. That was fun, right? If I was walking through the museum and it was this lady versus like the Mona Lisa, well, my amateur brain would be like, oh, Mona Lisa, right? But she has a great story. So she was painted by Eugène Delacroix. He was a French artist in Paris from 1798 to 1863. Here's the story. Now, I should say, if you go to the museum, you're not going to hear this story, but this is a story that a friend of mine who is a very smart person about art told me. She said, Delacroix's affection for Madame Raisonnet, an aunt, is expressed through the frank tenderness of this portrait. She was once known for her beauty. Some 30 years before the date of this portrait, she served as a lady-in-waiting to Empress Josephine, and having caught Napoleon's eye, engaged in a brief liaison with him. After she died, Delacroix wrote to Georges Sand that each of the beings necessary to our existence who disappears takes away with him a whole world of feelings that no other relationship can revive. Now, I mean, can you imagine someone writing that about you? I mean, really, I hope someone writes that about me someday. Hi, honey. We'll see, I guess, if I go first. If I had seen this piece in a museum, among lots of other beautiful pieces, I wouldn't have known anything was special about it to my untrained eye, right? Click. But now that I know the story, it makes me appreciate her so much more. It makes me appreciate her as a person, but also the techniques that were used in order to create this painting. If we look at the next slide, why do I bring this up? Well, in astronomy, I think there's a similar situation. We can look at an image like this, and this is Saturn, one of the most beautiful planets in the world, yes? And we can look at that and think, this is a beautiful image taken mostly in ultraviolet light. I think there's a little optical and infrared in here as well, but mostly ultraviolet light. And we can see that Saturn is being backlit by these rings. It's a gorgeous, gorgeous image. But right over here, I think a single spot, a single pixel, one little bright white spot. And that is Earth. And this was a picture of a spacecraft that was looking back on Saturn and saw, there's the one. I was not too far off. It's a little pixel right here. I can show you on my screen later if you like. So pretty much everyone who's ever existed, right, has been in that one single pixel. So I can talk about the science of this object, and I'm happy to do that. But I love the context that we're able to talk about when we understand a little bit more than just the data behind the images. So click. So So it's been 20 years since the Chandra Observatory was launched on Space Shuttle Columbia. Click. We've looked at a lot of different kinds of data of the universe, all of these amazing ones and zeros that look not like so much right here, but that can be translated into these amazing, beautiful objects to both learn from and then also admire. We looked at Cassiopeia A specifically, our good friend, the exploded star, 10,000 light years away, 10,000 times 10 trillion kilometers. This is the very first image that we ever got from Chandra, and this is it 20 years later. All of that amazing data. We're looking at the difference. The previous frame was maybe 1 hour of observation. This is 2 million seconds. That deep data gives us a lot of information to work with. Oh, that's me. Why do I have that in there? So we've gone from looking at it in 2D space to 3D. We've gone to holding it to walking inside it. Oh, press play on that one. It might not be auto. The little play button on the lower left. This is my newest project, made with Unity. This is an augmented reality version that anybody will be able to use with their cell phone. So even if you don't have access to VR equipment, you can still look at a 3D model in space in your room as you're walking around it. Access, I think, is a really important point to me. Click. And I write books. That's it. So I guess I would just say thanks again for having me today. I hope you enjoyed this little exploration through the kinds of data we get. And if you haven't gotten the 3D model yet, let me know. In the back, I have one virtual reality headset. I like to travel light, so I only brought like a couple books and one headset because it's just heavy stuff. So if you want to take a look at some of the books, or if you want to take a spin through Cassiopeia A yourselves, just let me know. I'm going to try to keep it very short so everybody can have a chance if there's a lot of people interested. If you want to find out more, some of the projects that I talked about, here are all the reference URLs. I just have to say that Chandra does not endorse any commercial product, because I know I do show some different kinds of equipment in my talk. Here's the contract number, and there's my website if you're interested in learning more. Thank you again. So I think we're going to take questions, but we don't have a mic, right? Just
the mic is out.
Oh, it is.
I'm going to bring up the lights and bring up the screen, and please ask questions.
Okay.
Yeah. So how do we know the chemical makeup of materials?
So we take spectral information when we're making all of our observations, and that spectral information, it's like the DNA fingerprint of light, and that tells us what the emission is. So we know from the emission whether it's iron, whether it's calcium, whether it's silicon, etc. So with every picture we get, we also get the fingerprint, which is really, really important information. To be honest, most of the science comes from the fingerprint versus the image. Yep. That's a great question.
Is each supernova unique to itself? Or is it
Yes. So they're kind of like snowflakes in a way, right? They're sort of unique, but there's also similarities. There are, I have to be honest, when I was young, I wanted to go into medicine for a long time, and I'm so glad I didn't, because the human body is like crazy, right? I mean, I don't know how doctors do it, because like no person is at all like anyone else, and it's impossible to make those kind of diagnoses, right? With stars, you at least know if a star is a certain size, what it will do, right? So you do have some predictability. But once a star goes supernova, the shapes and the structures that can take after the supernova are incredible. And that's where the snowflake part comes in.
Can you measure the amount of time in the past when the star initially exploded?
Yes, so you usually know, for example, a star of a certain mass will have to explode by a certain age because of gravity, essentially, in the basic physics.
When you discovered it, can you look at the star mass
And understand how old it is?
how old that
Yes, yes. So, for example, Cassiopeia A that we've been looking at, the explosion happened about 320 years ago in our time. It's 10,000 light years away, so 10,000 plus 320. Yep. So if we went there in our spacecraft right now, if we could, which we can't, it wouldn't look anything like it. It would probably be dissipated out to a huge amount, so you couldn't see anything up close, if that makes sense. In this case, we have the benefit of being farther away. Yeah.
There is no sound in a vacuum, but when a star explodes, can you image, can you somehow project the sound that it might make?
Yes, sort of. We can, through data sonification, actually translate the information into sound. We can also see things like black holes, for example. They have these vibrations in space that they're essentially singing, but it would be like 57 octaves below C, right? So no human ear could hear it. And of course, there's nothing for it to bounce off so that our ears could have access to it. But if somehow we could hear that low, and if somehow there was a way to hear the sound, black holes sing. We just can't really access it. Yep.
Showing us for 20 years. What are you going to be showing my grandson?
Well, I hope Chandra's still around. I really do. We are working on new X-ray telescopes that will have higher resolution, better collecting area, faster survey speed. Hopefully we'll have the money to put one of those up in space and to develop it. I don't know. If we do that, I imagine getting 3D maps of supernova remnants will be so simple compared to what it is now. We'll find out more about the very youngest black holes way, way, way back in the universe that we have no access to right now. I mean, there's so much exciting stuff that we can do if we have more better data. So what your grandson will be able to do, I can't wait. Can't wait. Who else?
I just wanted to tell you that was an awesome presentation.
Thank you.
I
Thank
love
you.
3D.
Thank you. So do I, if you can't tell. I love 3D stuff.
I do.
All right, in the back. You had your hand up first. Yeah.
As an amateur astronomer, the famous objects we always look at is the Ring Nebula. Have you done anything with that?
I have not, but I have actually seen some other person, I forget the scientist's name, do a 3D simulation of the Ring Nebula. And someone else did it for the Nebula, and I think there was one more nebula that I'm missing. So I don't have that data, but I know there have been simulations. I don't think there's observational data for that yet, but mathematical simulations instead. So something like that's coming. Again, more better data. I think we'll be able to do these for a lot more objects. It's amazing to me, like when Chandra launched in 1999, if you would have told me in 20 years' time, I'm going to be learning how to 3D print and code in VR so that I can walk inside a dead star, I would never have expected that that's what I'd be doing. So I really look forward to seeing, I mean, your question about what happens in the next 20 years, I just can't wait to see what those technological achievements will bring. Yeah, question.
Organic molecules and chirality.
What about it? I think you're getting to above my pay grade stuff.
Area.
I don't think so, but I'm not sure. That's not my area, so I don't know that I can really answer that. Yeah.
Is there an international standard for where you clean the data, validate the data,
Oh.
push it into the 3D presentation layer? So like when we're looking at, say, NASA, the projections, we're going to see in the presentation layer.
That's a great question. So that is an excellent question. Data standardization, as far as color coding, no. And the reason that that is the case is because each data set needs to have its story told in a way specific to the data. So it's been very hard to standardize globally, if you will, universally, to use the word, I guess that would be more appropriate, in a way that really makes sense for the data. That said, there are guidelines that I think a lot of people who do this work do follow. And of course, there are other areas that have been standardized, like the way we code our metadata. For example, those are standards that we follow. They're called AVM metadata standards. So by the time we get to the 3D space, and you've probably seen here, there's a lot of different versions. Each time I work with a new person, a new student or whatever, like a color might get changed because the blue is really not showing up in VR space, even though it showed up just fine in a desktop environment, right? So for all of those stages of even one data set, you might see variations across it, and it's because the data or the platform kind of demand it.
So if you accept data from an external source, or you would go through the validation and cleaning process again?
Well, the very baseline, every bit of data that's in a NASA archive has gone through a baseline, yes. But as soon as you get out of there, which is what everybody does their own stuff to the data, that's where their standardization breaks down. Yep, that's a good question. Yeah. Yes, so Hubble, for example, looked at Cassiopeia A that we looked at different times that Chandra did, but close enough that you can compare them in a reasonable way because the data, the object itself is changing slowly enough that those differences don't matter. But there are actually coordinated observing campaigns for objects that the change in rate of that object matter more. So for something that's going off like a gamma ray burst, or for a very active black hole, something that's really, really moving in a smaller concentrated area, then you have telescopes that are programmed to look at them at the same time thereabouts. So that way the data that's going to be stacked is going to be almost collected at the same time. Yep.
How much time do you spend looking at one supernova, collecting data before you move on to another one? And how long does it take you to eventually get back to that first one? And then the second one is, how do you find supernovas?
So I feel like some of these supernova remnants are just like my old friends, right? Like Cassiopeia A, I will put it aside for a little bit if there is something new coming into my desk that I really need to get to. But it's one of those objects, the information is so rich that I just keep going back to it to see like how much lemonade can we make from this. You know, I want to squeeze out all the lemon juice from that data set. As far as how we discover supernova, they kind of point the way, to be honest. We know, for example, with stars of a certain age that they will go supernova at some point, but the time frame is huge, and time frames of stars don't make any sense in human perspective, right? With Eta Carina, it'd be cool if that star exploded sometime while I was alive, but it could explode in 50,000 years, and I'll have missed it by a lot, right? So supernova 1987A, the second object that I showed you, that one was discovered in 1987 because, boom, it went off in the sky. We hadn't expected it to go off, but it did. There are so many stars, and there's so much to learn about them. Prediction is very hard. Yeah.
Does vortexual mathematics play any part in your calculation?
Does what?
Vortexual rod and coil?
No, not at least not in what I do. It might be someone else though. Yep. Any other questions? Oh, in the back.
So when a supernova explodes and spews out all this iron and sulfur and silicon and everything, what's left in the core?
So it depends. It depends on the size of the star. So the fate of a star depends on its mass. Stars like the sun don't go supernova at all because they're too small, which is a great thing for us. I mean, the sun will change, but not for like 5 billion years, so we're cool for a while. However, with stars that are really massive, like, I don't know, maybe 100 or more suns, when those stars explode, they obliterate everything so that there is nothing left behind. Stars that are slightly less massive than that, when they explode, they tend to form a black hole. Stars like Cassiopeia A, they tend to form the neutron star, which is left over, and you can't really see it. Go, there it is. The neutron star, that's in between. So it really depends on how massive that star was to begin with as to what end result you're going to get. But way more predictable than human bodies, which is why I like astronomy. And very good choice not to go into medicine, because I think people would have driven me crazy with their bodies, you know. Any other questions? Yeah?
I guess I have a dozen questions.
Just one, please.
So one that interests me, that maybe you can answer, is 1987A. So I can't remember back then whether it was 6 months before, but there was, I think, maybe 2 or 3 neutrino detectors on Earth. And they picked up a flux. I think at the American site, there was an Italian site, probably a Russian and maybe Japanese site for neutrino detectors.
Yep.
Which are, I don't know how many thousands of feet or hundreds of feet. What is it? Tetrachloride with photomultipliers and that sort. That's about where nothing else can get there except for neutrinos. So it's a pretty dry area for looking at them. It's pretty background noise. So they got this flux, and they thought that it was an anomaly. I think in the United States, and then they correlated it. with, I guess, the 2 or 3 other detectors, and and it was coincidental. You were probably still very young.
I think.
But, I know about it. But, so anyhow, they didn't know what it was. It was like, holy, crap. What was this big flux of neutrinos? And these type detectors were pretty new, So that's why they thought it was an error at first. And so, anyhow, I think like maybe 7 months later or 8 months later, of course, a Peruvian astronomer, amateur astronomer, was the first one to see. Mm-hmm. Yes, you know the story. Mm-hmm. And then they correlated and they said, holy crap again. What we saw 6 months ago was the neutrinos that got here before the light. So for Cassandra, or Chandra rather, which by the way I was part of some of the detector development.
Oh, fantastic.
I can't remember whether the guy was working on zinc cadmium telluride or detectors. But anyway, so yeah, anyhow, it was a cadmium telluride semiconductor. So, or Chandra. Anyhow, has anything been done in this area of trying to resolve this whole maybe neutrino thing?
I'm sure there has. I mean,
with Chandra.
With Chandra?
It's the highest frequency detectors, telescopes that we have, right?
Yeah, I don't know a ton of studies on neutrino information specific to progenitor supernova remnant information.
Been connected with,
perhaps.
Say,
You'd have to Google Scholar it.
Yeah, ARXIV might work, but not Google Scholar. Yeah.
Sure. I guess what I would say is, like, when Chandra was built and launched, there are a number of fields that were not in existence at the time. Things like exoplanet research, multi-messenger astronomy, and detecting gravitational waves, for example. Chandra has actually been able to come to the plate each time. So Chandra now studies things like host stars for exoplanets to understand the star habitability. Chandra studies X-ray outbursts, the first detection of X-ray light from neutron-star mergers that give off gravitational waves. So the point of all of that is that even though Chandra was not necessarily built for specific answers to some of these questions, it has been a very nimble and high-quality device to be able to study them. So I'm sure someone has studied them. What they found, I don't know. You'd have to look it up. Any other questions?
How much longer for the space cake?
That's a great question. I mean, I hope for a while because it's like my job, so I don't want to be like laid off or anything. Chandra was built. Yeah. Chandra was built to last for 5 years and has lasted 20. When Chandra was launched, because it goes a third of the way to the moon, it had to work perfectly. There were no takesy-backsies with Chandra, right? It had to work right out of the gate, and it amazingly did. Since then, all of the people on the ground, the operations control centers that essentially code the spacecraft every day, have taken excessively good care of it to make sure that even if something is a little bit problematic, they essentially upload new code to figure out a way around it. They are like the X-ray astrophysics detectives. So Chandra to this day remains very high efficiency and in very well health. Of course, a meteor could knock it out in 5 seconds, and I wouldn't know just yet. So we don't know anything. I will say that NASA's been committed to keeping Chandra running. They've shown us that they're very committed for that, for which I'm very grateful. There's no new telescope for X-ray astrophysics coming very soon. So I think it behooves the whole X-ray astronomy community to be able to benefit from Chandra. So hopefully 10 more years we can get out. I would love that. Fingers crossed. Yeah, maybe last 1 or 2. I don't know how far you guys want to go, but go ahead. Sure.
I'm a public school educator. For the past few years, I've been working on trying to get kids more interested in coding, particularly girls.
Oh, great. Oh, we should talk.
Yeah, okay. So I'd love to share a story, but I'm looking online
Yes.
and I don't see that jump that you made. I don't see any details about that jump you made from bio to coding.
Sure. So, I mean, I can give you the 2-second version, which was I was getting bored in biology and I was just talented in computer coding just because I'd been messing around with it for a while. And I found a great professor who just kind of brought me under his wing and threw me into the computer coding world and had me teaching a class within a semester. I mean, it was a very strange kind of transition of having my own background in it and then realizing I have a skill here, let me do something with it. So for me, being able to translate other kinds of scientific data into something usable through computers was just something that I had a natural knack for. However, I've actually, with Google, built a couple activities to help show other kids how you can do this type of work. And I think my assistant sent the handouts. I think they're back on the table back there. But if not, I'd love to talk to you more, because I do like Hour of Code, Girls Who Code, Black Girl Code activities, all those groups I work with, and love it. So thank you. Great. Any other questions? Okay. Yeah.
One of the things that I think you get just fabulously lucky at is that it has
That's right. See, doesn't everybody remember it now? I said it.
It's only 10,000 meters away, and yet with the other nebula one study was something like 160,000. Is there a practical limit on distance where you can say, oh, this would be fabulous to 3D image, but honestly, we just don't have the answer?
Yeah, and pretty much Supernova 1987A is about as far as we can go right now with the resolution we have for the type of information we need. However, there are other telescopes being launched that can help give us some of that velocity information that we can't necessarily get just from Chandra. Sometimes you have to be able to supplement it with other telescopes, right? All of these telescopes play very well together in the sandbox. You really need to have all that different kinds of information in order to make these 3D maps. So as new telescopes are launched that have specific detectors for velocity information, we can go a little further, and then Chandra observations can then constrain them so that we understand what that 3D map might look like a little bit better. Yeah, but that's a great question too. It's definitely the limits.
We'll take one more question.
Right, one more? Anyone I haven't heard from yet? Just, okay.
Okay, I got a second question. It's a sheer volume of data.
Yeah.
We're always looking at a small subset of it. What's the most exciting thing that's happened from new technology over the 20 years where somebody went back and re-looked at something? You go and see something new.
So people go in the archives all the time and make discoveries. That is, honestly, it's happening at a pretty high rate. When you have an archive that is as rich as the Chandra was, and the others as well, Hubble and Spitzer and the other telescopes, you're just constantly being surprised with new gold nuggets, right? The other thing that I like about that kind of archival system is that if some other new telescope discovers something, you can then go in the Chandra archives and get the data of that object and see what it was doing in X-ray light. That object might not have been of interest before the discovery in infrared light or optical light or whatever it is, but then you have this amazing map that you can go back and get observations from Chandra. That has been very valuable as well. So sometimes it's just, you just don't know, because the universe is so big, right? You don't always know what exactly it is you're looking for, but if someone else finds something that you can latch onto and compare your data with, you can get a whole other piece of the puzzle. So for me, that kind of multi-wavelength astronomy, participation, cooperation in the scientific field, it's just an absolute treasure. Yeah, that's a great place to end. Archives are awesome.